Thank you for the opportunity to present this proposed U.S. Forest Service hazard classification methodology to the Interagency Committee on Dam Safety. I am an Assistant National Dams Program Manager for the U.S. Forest Service that focuses on policy, best practices, and special projects. The agenda will cover FEMA guidelines specific to hazard potential, definitions specific to the proposed methodology, introduction to the conditional probability model for loss of life, and a draft spreadsheet that covers the calculations of the conditional probability model for loss of life. Dam safety programs with low population densities downstream and smaller dam heights typically only have a small number of locations of interest downstream where population may reside. This highlights the need to further quantification of probable loss of human life of one or more. Programs with higher population densities and larger dams likely do not have this issue due to larger exposed populations. The proposed methodology determines probability of loss of life at all locations of interest where population reside temporarily or permanently that are exposed to the hazard. When the probability of loss of life at any location of interest equals or exceeds 50%, it assumes that at least one life loss is probable, which is denoted in the red box as probable to certain on the left side of the slide. FEMA 333 definition of probable is described by three other words: likely to occur, reasonably expected, realistic. Appendix A of FEMA 333, titled Background, states the term probable loss of human life is defined to signify one or more lives lost. The term probable is specifically included to indicate that the scenario used to predict the loss of human life must be reasonable, realistic, not contrived. This adds context to worst case probable scenario as being reasonable, realistic, and not contrived. In the definition for high hazard potential, the probable loss of human life is further clarified to exclude the casual user of downstream or upstream area in determining the potential for loss of human life. This statement excludes locations of interest that are only occupied for short periods of time. In my opinion, probable with regards to loss of human life should focus on probability of loss of life at a location of interest, not exclude sites from analysis based on short periods of occupation. Locations of interest that are excluded from analysis may have high levels of flood severity with regards to exceeding stability thresholds or high rates of rise of floodwaters that may show high probability of loss of life. In these cases, the location of interest with high vulnerability to life loss would not be identified to support determination of hazard potential classification or future mitigation measures like restricting access or warning signs, which have legal ramifications. Exclusion of locations of interest with low occupation times potentially conceal locations of interest that may have high vulnerability to loss of life. A good example would be roadways and public access points near the toe of the dam. The proposed methodology considers all locations of interest regardless of low occupation times, which is common on U.S. Forest Service roadways and in day use areas. Based on the prescriptive approach in FEMA P-94, a high hazard potential dam should pass a probable maximum flood, as shown in the table on the top right. Additionally, significant hazard dams have considerable direct losses, but no probable loss of life and must pass a 1,000-year annual exceedance probability storm. A low hazard dam does not have considerable direct losses or probable loss of life and must pass a 100-year storm. Below the orange line shows proposed U.S. Forest Service guidelines. Direct losses in the form of economic, non-recoverable environmental and lifeline losses are proposed at $3 million, as shown in the third column from the left side in the lower table. When probability of loss of life and direct losses cause conflicting classifications, the most conservative controls. There is also discussion on removing the dollar threshold from direct losses and replacing with a rubrics criteria or multi-attribute model at a location of interest or for the dam. With this proposed methodology, probability of loss of life ranges are provided for low hazard, significant hazard, and high hazard, like shown in the second column of the table below the orange line. It would be possible to provide all classifications based only on probability of loss of life and reduce work effort for classification by not going into quantification of direct losses. Appendix 9.2, relationships between probability of loss of life and economic damages in Dr. Junkman's thesis show a correlation value of 0.95 between the two for data he analyzed. This is not what is being currently proposed due to current FEMA guidance, but would be worthy of future investigation when considering updates to FEMA guidance. Determining probable loss of life at a location of interest has a large impact on capital cost of spillway compliance and should be informed with as much information as possible. For example, the U.S. Forest Service has one dam in Region 8 and one in Region 9 that are in the design phase. They are currently assessed as high hazard, denoting probable loss of life depending on the factor thresholds, like stability thresholds. The dam could be considered a significant hazard. It has been estimated by consultants that to pass the probable maximum flood as a high hazard would cost $20 to $30 million for each dam. If the dams were classified as significant, it is estimated to cost $4 million or less per dam. This is an 80 to 90% reduction in capital costs. Costs should not drive methodologies, but all dam safety programs are financially constrained to some level, some more than others. A possible solution to this would be to consider other factors conditional on stability thresholds at the peak of the event. Three documents are shown on this slide in our current guidance on estimating consequences of a dam failure. Human consequences are reported in the number of estimated fatalities, not probability of loss of life at a location of interest. This is likely due to the methodology supporting emergency management and risk assessments, where the quantity of losses are needed versus the probability of consequences occurring, which is needed for the determination of hazard potential classification due to probable loss of life of one or more. The construct of current methodology bases loss of life from stability thresholds at the peak of the event and is not conditional on other factors of explanation. For example, probability of population presence and probability of escaping or being rescued prior to achieving the stability thresholds at the location of interest. Probability of loss of life due to loss of stability could also be conditional on the level of debris within the floodwaters, which is currently not being considered in this proposed methodology, but is derived in Ramsbottom 2004. Probability of loss of life can easily incorporate stability thresholds that are conditional on other factors. The incorporation of probability of population presence is important when dealing with transit populations for roadways, trailways, and other areas that have lower occupation times. In addition to this, dam failure events are dynamic in nature, and the water rises at different rates, which affects the population's ability to escape or be rescued once the hazard is identified or at the time of initial exposure prior to the stability threshold exceedance. Research has shown that flood events like flash floods are more dangerous than other flood types. likely due to having less time to react to the hazard. Current guidance on inundation mapping to support analysis in FEMA P-946, Federal Guidelines for Inundation Mapping of Flood Risk Associated with Incidents and Dam Failure, states analysis should continue until the flood wave is within the confines of high water banks for non-hydrologic scenarios, like the proposed scenario that we're basing the classification on. This requires long downstream reaches for analysis based on the storage of the flood wave. Over long distances required for this analysis, attenuation of the flood wave occurs and rates of rise of floodwaters decrease and the flood wave as the flood wave moves downstream. This provides more time to react to the imminent hazard the farther the population is from the breach. Research has shown that fatality rates are higher when rates of rise are higher. Warts, 1992, Junkman, 2007. Stability thresholds can be conditional on not being able to escape or be rescued prior to stability thresholds being exceeded. Definitions for the proposed methodology. Scenario hazard. Flood waves from a dam breach or misoperation when pool elevation is at the dam crest. Exposed area. Maximum inundated area of a flood wave due to scenario hazard. Location of interest. Location with an exposed area where a group of people, one or more, may reside temporarily or permanently based on historical use. Stability thresholds. Maximum depth and velocities during the peak of the event that are large enough to cause loss of stability in whatever state the population's in. Definitions continued. Probability of population presence at a location of interest. Percent of time during a day, 24 hours, that the location of interest will be occupied. Estimated population at location of interest. Maximum daily estimate of population at the location of interest, typically estimated as the maximum occupancy. Exposed population at location of interest. Population exposed to scenario hazard that escaped, were rescued, or are deceased. Direct losses, economic, non-recoverable environmental, and lifeline losses. Definitions continued. State of population at a location of interest. The state of population is used to categorize stability thresholds. It's different if you're on foot. The velocities and depth that it takes for you to lose your stability on foot versus in a vehicle, in a mobile home or RV, or in a residential commercial structure are different. Use of location of interest. Use of location of interest is used to determine probability of population presence. Day use areas, look at during daylight hours. Overnight and day use areas, assume occupation through the whole 24-hour period of a day. Route is obviously temporary, would be the estimated time at that specific location using the route. Time available for escape or rescue is estimated as time of arrival of the flood wave at the location of interest minus the time to achieve the average stability threshold depth of 2 feet. This also corresponds to the rate of rise from 0 to 2 feet at the location of interest. Model for estimating probability of loss of life for a dam failure. It considers multiple qualitative factors for explanation. More information leads to more informed analysis and decision making. Repeatable and measurable, which lends to automation of the process with review by subject matter experts and standardization across all regions of the U.S. Forest Service. It provides the ability to make informed decisions about the dam by distinguishing differences in vulnerability across the total inventory that has been classified with this methodology. It provides the ability to prioritize dams based off of vulnerability scores for follow-on prioritized risk assessments to inform the program on probability of specific failure modes occurring. It provides the ability to prioritize emergency response operations in a resource-constrained environment based on probability of loss of life at all locations of interest. The proposed methodology uses standardized breach hydrographs based on dam type, dam height, and storage that assumes the peak flow rate occurs at 75% of the breach formation time for earthen embankment dams. A dam type with the same height and storage across all regions in the U.S. Forest Service will be assessed for classification based off the same breach hydrograph. In the future, U.S. Forest Service may consider including site-specific information like soil types that affect the breach formation time and the relationship between formation time and peak flow rate time. The proposed standardization lends to automation of the hazard classification process with review by subject matter experts. A current pilot study classifying 33 dams with this automated, standardized, qualitative process is showing a 90% cost savings from historical cost of determination of hazard potential classification. In a resource-constrained environment, this allows for more resources to be applied to analysis of spillway compliance, upgrades, and prioritized risk assessments based on vulnerability scores in the inventory. This slide shows the outcomes of the methodology prior to explaining the methodology itself. So if you take a look at the left side, that denotes an inundated area. You can see 6 different stars on there. That's location of interest where population historically has resided either temporarily or permanently. Each location of interest is going to have a conditional probability of loss of life assigned to it. You can see that in the second column. Out of the 6, the highest probability loss of life is shown as 75% at location 4. That would control the maximum probability of loss of life at all locations of interest, which is what it will be used to determine if there's probable loss of life of one or more, and it's considered a high hazard dam. The third column shows the estimated population in each location of interest, and then you can see at the bottom it's summed up to the total estimated population for the dam. The last column on the right side is the weighted conditional probability of loss of life at a location of interest. This is used to ultimately determine the dam's vulnerability to human consequences. So how do we calculate weighted conditional probability of loss of life? That will be explained in the next slide. But basically at the bottom you can see it's summed up. You see summation of total weighted conditional probability of loss of life for the dam of 51, and that's in a percent form. And you see the dam's vulnerability to human consequence score. The summation of the total weighted conditional probability loss of life for the dam and the total estimated population for the dam are used to determine the dam's vulnerability to human consequences score, which will be explained in how to calculate it in the next slide. You see the last part is estimated losses, economic losses, non-recoverable environmental losses, and lifeline losses likely greater than 3 million or not. It's a yes or no. Looking at the box at the top right side, the weighted conditional probability of loss of life for a location of interest equals the conditional probability of loss of life at the location of interest times the decimal percent of the total population at that location. Second box below that, summation of weighted conditional probability loss of life for the dam. So that's summing all the weighted conditional probabilities of loss of life at locations of interest. And then you see the dam below that, the next box, dam's vulnerability to human consequences score equals the summation of the weighted conditional probability of loss of life for the dam in decimal form times the estimated population for the dam. This is used to rank vulnerability of the dam with regards to the rest of the inventory that have been classified with this methodology. At the bottom right, you see the U.S. Forest Service proposed policy. You see hazard potential classification, high, significant, low. You see the probability ranges for each one of those classifications. You see the economic lifeline losses, and then the inflow design flood capabilities without overtopping. The conditional probability model assumptions. The assumption is that people will avoid imminent hazards. Factor 1, probability of loss of life based on stability in floodwaters. This is the backbone of the methodology. This is the single factor that people currently are using to determine probable loss of life at a location of interest. It reports how likely human population will lose their life based on losing stability in floodwaters, which is conditional in this methodology on population presence at a location of interest and not escaping or being rescued. Take a look at the table on the left side, loss of stability criteria. Based on the state of the population at the location of interest, stability criteria will be different. On foot or in a tent, in a vehicle, in mobile homes or RVs, or in residential commercial structures, all vary on loss of stability criteria. Stability criteria is measured based off of the maximum depth and the maximum depth times velocity at the peak of the event. If neither one of those is exceeded at a location of interest, the probability of loss of life based on stability in floodwaters would be 1%. If one is exceeded, then it's 50%. And if both are exceeded, it's 100%. The table on the left side for loss of stability criteria is referenced from FEMA DSSY's Light Technical Report, page 88, Fenberg 2017, which is supported by Cox 2010 and BC Hydro 2006. Historical fatality fraction ranges between 0.5 and 1% when stability is lost. Dr. Junkman, 2007, thesis review of data supporting life sims, page 172. Factor 2, probability of population presence. This reports how likely human population will be present at a location of interest when flooding begins due to a dam failure. Use of the location by the population. If it's a day and night use area, it's estimated at 100%. If it's a day use area, assuming 13 hours of daylight, it's 54%. Routes for vehicles or foot traffic are based on uniform traffic rate, speed, and length of inundation. Probability of population presence on a route. You can see the equation, maximum daily groups per an hour divided by free flow speed times inundated road or trailway length equals groups per inundated road or trailway at the onset of the flood wave at the location of interest. An example of estimating population presence on a route, if the vehicles per an hour were 15 miles per hour, speed limit or free flow speed was 35 miles an hour, inundation length was 0.1 miles, you would have a 4% chance of population presence. When using the equation, if it exceeds 100%, what that's saying is that there's one or more groups that are inundated. That will not, if it exceeds 100%, it stays at 100%. So because you're saying that there's a 100% chance of population presence. Also, note that we use the average annual daily traffic to determine vehicles per hour when available. The average annually daily traffic is the total traffic volume passing a point or segment of the road in both directions for a year divided by the number of days in a year per the simple average method and can be used to estimate maximum daily vehicles per an hour. Typically, traffic is assumed to only occur during an 8-hour period of the day to simulate a peaking factor for maximum vehicles per an hour. Factor 3, probability of no escape or rescue. This reports how likely human population will not be able to escape or be rescued at a location of interest when flooding begins due to a dam failure if occupied, if population is present, based solely on time to achieve average stability threshold depth of 2 feet minus the arrival of the flood wave at the location of interest. Global statistics show that probability loss of life at a location of interest increases when rates of rise of flood wave increase. For example, flash floods, Junkman 2007. Flash floods are classified as the most dangerous type of flood per National Weather Service in Graham's 1990 data for dam breaks. This table was developed for this proposed methodology and is assumed to be the first guidance developed to estimate population's ability to avoid the imminent hazard prior to stability thresholds being exceeded. If you take a look at the left column there, it goes from very high at the bottom to very low at the top. It has corresponding rates of rise per 5 minutes. The time to achieve that 2-foot water level from 0 at the location of interest and depth to 2 feet. For very high, it takes 15 minutes. For high, it's between greater than 15 minutes to an hour. Medium is greater than an hour to 3 hours. Low is greater than 3 hours to 6 hours. And very low is greater than 6 hours. You can see the corresponding probabilities of chance of no escape or rescue on the far right side. These probability values are subjective and supported with historical flood events typical of U.S. Forest Service environments. Case study 1, U.S. Forest Service Albert Pike Recreation Area that had a flash flood event on June 11, 2010. Historical data provided the flood hydrograph by USGS. Locations of 17 of the 20 fatalities were provided in a news article by Arkansas Democrat Gazette dated November 22, 2010. Data verifies RV campers did not have time to escape or be rescued prior to exceeding stability thresholds. Locations of the 17 fatalities used in the case study are shown in the figure. A HEC-RAS 2D model with 1 meter digital elevation model with USGS flood hydrograph was used to determine time available for escape or rescue prior to achieving stability thresholds, depth, and depth times velocity at loss of stability. Time of loss of stability for L1 was reported during a phone call at 2:38 a.m. on June 11th. Comparing results of the model to probability of no escape or rescue table on slide 17 shows flood severity based on rate of rise at the 5 locations of interest is considered very high with a probability of no escape or rescue at 100%. Very high is assumed to have rates of rise of 0.67 feet per 5 minutes and less than 15 minutes to achieve stability thresholds. Column 2 of the table shows estimated rates of rise ranging from 0.83 to 1.11 feet per 5 minutes and 9 to 12 minutes prior to achieving stability thresholds. Stability thresholds on slide 13 and corresponding estimated probability of loss of life based on loss of stability, conditional on the population presence and no escape or rescue, are also supported by the case study. In this proposed methodology, probability of loss of life can be explained by probability of population presence and probability of no escape or rescue given presence, and probability of loss of life based on stability in floodwaters given presence and no escape or rescue. The multiplication rule of probabilities allows the 3 different probabilities to be multiplied together. The probability of A and B and C at a location of interest at the onset of inundation equals probability A times probability B given A times probability C given A and B. When those are multiplied together, the total probability of loss of life of 50% or greater at any location of interest denotes high hazard potential due to probable loss of life of 1 or more people. The current version of the spreadsheet is shown in the slide. The green highlighted cells are inputted, and the light blue are calculated outputs. Future versions will likely have data forms for the inputs to increase ease of use. Note the lower portion showing maximum probability of loss of life at any location of interest that determines probable loss of life of one or more, and dam's vulnerability to human consequence score.